So these coordinates we calculated are -1, 3, and 2, 6 just by plugging in. Let me know if this red is too hard to read. And so the slope through any 2 points is just y2 minus y1 over x2 minus x1. And that from before, it's the difference in the y coordinates over the difference in the x coordinates. But for this one, but you're calculating y by, call this b and call this a, and the y coordinates are computed by the function, and y2 gets replaced by f of b and y1 by f of a. So this formula, y2 minus y1 or x2 minus x1, becomes f of b minus f of a, the difference in the y coordinates here, over b minus a, the difference in the x coordinates here. So they're just calling them b and a instead of x2 and x1, and then f of b and f of a instead of y2 and y1. It's the same thing. You calculate those, the difference in the y coordinates, 6 minus 3, right? The difference in the y coordinates over the difference in the x coordinates, 2 minus a -1, because it's just 3 over 3. Oh, this is a slope of 1. Right? That one look all right. Let's make sure that that's clear. We didn't do one quite like this. I can't do all the problems in here. There's not enough time. So bring me the ones that are difficult and send them online or whatever. Email. A number of you are using the option on there to send me questions when you're stuck on the homework. And I'm trying to answer those. Here's another review problem that I put up on the board. Is this one. I told you this is the last one in the section. I think it's pretty hard. But it's kind of good because this is the kind of thing you do with actual calculations in the sciences. When you launch things into space, the escape velocity satisfies this equation. 1/2 mv squared is actually the kinetic energy. And gmm over r is actually the potential energy. And the idea is when you have escape velocity, these two are equal. You have just enough energy of motion to overpower the potential energy from gravity. So you just overpower gravity exactly. That gives you just enough velocity to keep going forever. If you launch with this velocity v, it will go out to infinity and reach there with velocity 0. So you're given, you don't have to know all that. This is 1/2 mv squared. I thought you might be interested. Is g mm over r squared, where these numbers are all constants except for v. You're supposed to somehow intuitively know that. All these are just fixed numbers. We call them constants when they're fixed numbers. Except for v is the velocity. And so the first part is solve for v. Solve the equation in terms of the other variables. Solve for v in this equation. Right. Again, when you have a square of a variable you're looking for, and it doesn't occur anywhere else, you just isolate. We started this last time, but I started it in a mess and I left it in the middle. So I'm going to do it better this time. I'm going to complete it. You multiply by the reciprocal of this number, right? This is m over 2. I'll multiply by 2 over m on both sides, and I'll get v squared equals 2 over m times g m over r squared. Multiply both sides by 2 over m to cancel. So I isolate v term. What's a term? Do you remember? Terms are things that are added together. So if I put them on one side, they'd be added together or subtracted. And so I've got, actually, let's not even put term. Let's just say isolate v. Isolate v, and I get v squared. Get it on one side. And now I'll take all numbers that has that square is this plus or minus. V equals plus or minus. Is this square root? And oh, wait a minute. When I multiply quotients, right, this times this times this is how you multiply quotients. You get m on the top and m on the bottom, so these actually cancel, right? Why do they put m on each side? It's mysterious, right? It comes into energy. This is the way it usually starts. So m's happen to cancel, which And you've got 2gm over 1r squared, right? Think of this as m times 1. So 2gm over r squared. So when you see this in your homework, this is what you do. Now, this can be simplified, and I neglected to check whether they try and simplify this. I guess we could try putting it in and see if they want it simplified. This is one of the trouble with mechanical software. It's intolerant of different ways of writing it sometimes. Or except they use not r squared, that's right. This is r because of the potential. R, and I should have written a capital R to mask the text. R, not R, so it doesn't really. And then because it's a physical problem and v is supposed to be the speed, the absolute value of the velocity, it's non-negative. So plus for speed only, you don't need to put the plus in. Put square root of 2tm over r for that answer. So that'll be that first part. But do that on your own and then look at the answer. Then it says the equation in part B that mg equals gmm over r squared. When I started, right? This one actually is the force of gravity, and this one at an arbitrary distance r from the Earth. And this is the force of gravity, mass times acceleration. Little g means acceleration at Earth's gravity. Just for your interest, if you're interested in physics, those are equal at Earth's surface, right? Gravity equals gravity. Here's gravity computed from gravity to the surface. Here's gravity computed. If you put r the Earth's radius, it will be the same. Gives the force of gravity at Earth's surface. You can use this equation to simplify it for p. So we'll just say this is known when r equals Earth's radius. These two will be equal. This is a general formula for gravity at any radius. That r equals Earth's radius. These two are equal. Once again, the m's can cancel, right? You divide by m on each side and get that. They say use this to simplify the expression. Multiply both sides by r over m. Very good to count. Say multiply by r over m, and you get gr over gr on the left because the m's cancel. Right. Equals r over m times g m over r squared. And the big M is like it's the mass of the Earth, and the little m is the mass of your object that's trying to escape the Earth. So now you notice these cancel over here. I already canceled the m's on the left. And one of these r's cancels this one. And we get gr is equal to gm over r. Oh, that's in here. I could replace that. Now let's say substitute your previous answer to simplify it. This is the kind of calculations that people often do. So this is application more than new math. So substitute, simplify previous result. Just put that in for gm over r. I'm asking you to do, and you get. I'll put it, this arrow means implies. So these two things imply that v is equal to the square root of 2, and I replace gm over r with gr. There's what I get with that one. And so the next blank is asking you to put You put GM over R equals GR goes in the one blank. And V equals this goes in the other. This goes in one blank. I'd actually write the expression for that right here. So V equals that much. When you go to put this in here, I wanted to make the point here that you can either type in by hand SQRT of 2. If they need you to put the multiply in there or not, 2 times, they might just need 2GR, they might need a time symbol in there. And try this with the class and we'll check. And think of that 2 times G times R probably works. 2GR might work also, one of those two things. But this here is computer programming in many languages for the square root. And so it will take that and convert it to a square root sign for you. Or you can use the square root sign on the menu. Calculator pad there. In other words, if you click on this thing here, this one, you can just try this, right? There's a square root sign, so you can put in the square root symbol that way. Yeah, I put 2 square roots. Let's try that square root 2GR, and I'll try not putting in the signs and see what it does. Oops. Oh, I just lost it. Good one. I just closed my page. I think I just closed my page. That's good. I'll just finish it here then. Anyway, you put square root 2GR into this blank here. And then it says, find the escape velocity from Earth. So they say Earth's radius is 6,400 kilometers. KM for kilometers. People in other countries say are kilometers in this country. This meaning thousands of meters, right? 1,000 meters, kilometers. And there are G is 0.0098 kilometers per second squared. Distance per second squared is actually units for acceleration. It's not clear in this class. You have to take your physics class, but distance divided by time squared is the units for acceleration. This is the acceleration of gravity near the surface. It's also 32 feet per second squared is another measure of it. But if you're measuring in kilometers per second squared, that's a long way. It's a much smaller number of kilometers than feet, right? Just how many? 32 feet equals 0.0098 kilometers is the idea. All right. The reason I put this up here is if you put in your own conversions, it's likely to give you the wrong answer. They rounded these numbers, so they rounded it to 2 digits, and you have to use the same 2 digits possibly. I don't know how tricky the machine is. If you put 32 feet per second squared and convert it, it might be a little different than that. Give you a slightly different number. But what you get when you put that in is you get V equals square root of 2 times 0.0098. Put those numbers they gave you in times 6,400 for R, and there's, you put those in and see what you get. And what you get is 11.2 and a bunch of stuff. They've rounded it to 1 significant digit. I think if you put in more digits, you'll probably accept it, but put in 11.2 and it works. That's what it's set up to do. And what are the units for this? Yeah, we've been using kilometers and seconds, so it comes out kilometers per second. Whatever units we're in here, you use here. And velocity is distance per unit time, right? It's distance divided by time is velocity. So you use a distance, kilometers, that was up here. Time unit, seconds, that was up here. I don't think they ask you to put the units, but some of the problems. So that's how you get the answer to that one. Then they have another one with the moon. I'll let you do this yourself. Moon is about a sixth Earth's gravity, so you get an answer about a sixth, a little over 2 kilometers per second. But this tells you if you get your rocket near the Earth's surface going 11 kilometers per second, it'll go on forever and never come back. It's kind of a fun problem. If you go that fast, gravity can't pull it back anymore. Any questions on that one? Well, I thought that was a hard problem on there. You kind of point out, you have to probably put in their numbers. It bothers me that some of these, they give you 2 significant digits, then they expect you to round it to 3 significant digits. That's actually bad. Now, once you round this to 2 digits, the result is including more than 2 digits. This, I think, is the actual answer. So they just left it that way. They should have put more digits in on each of these. But I got the same answer. Go. You've heard that before. If you multiply numbers with a given number of significant digits, you have to round to the number of digits as least of these. Okay. Questions on that one? I guess I said already. Now I want to do some new things. Fortunately, that's still up. All right. Hopefully. Today we want to talk about some more. This is not the right one. Talk about transformations of graphs, basic graphs that lead to these transformations. These I know you've seen them somewhere in previous algebra. Back there, please. I know you've seen these before. It really behooves you to be very familiar with these because if you go on and take another math course, these are used a lot. For instance, in calculus, if you're taking now, a lot of people take algebra and then trigonometry and then go on to calculus. You'll use these quite a bit in there, for example. Here are the ones they like to list. They list 8 of them. One of them is f of x equals mx plus b. We already discussed this one. What does that look like? If I give you an f of x equals mx plus, well, actually, let's even put it easier than that. They put this one, f of x equals x. Let's just do it this way. Y equals x. What does that look like? If I plot y equals x or f of x equals x, it looks like
just a
horizontal. Yeah, it's a 45-degree angle. A line splitting the 2 axes here. Well, that's it. Y equals x looks like that, right? If you're at x equals 1, you're at y equals x equals 2, you get y equals 2. So that's the basic graph y equals x, right? And then you have, I'm going to do one more here. Call this 1b. Y equals mx plus b. What if you have this kind of graph? What does this come out to be? We did this one. This is my fault. What does this come out to be? A line, the slope, m and y-intercept b. Remember, this is slope-intercept form for a line. Every line that's not vertical can be written in this form. And so it's a line that has, if you compute 1 unit over, it goes m units up because the rise over the run is always the slope, right? So you can also put rise over run. So it's a line like that, and it goes to a y-intercept b because if you plug in x equals 0, you get m times 0 plus b minus b, right? So it's a y-intercept b and slope rise over run m. So recognize that whenever you see it. That's a generalization of that one that they refer to a lot. the next basic graph is this one, y equals x squared. This one you've seen before in basic algebra. Looks like this. It's called the basic parabola. And if you compute some points on it, right? Put x equals 0, then y is 0 squared is 0. Put x equals 1, and 1 squared is 1. Right? Minus 1 squared is 1, and minus 2 squared is 2, and 2 squared is 4, excuse me. And 2 squared is 4. So you get these points on it, 0, 0, 1, 1, minus 1, 1, 2, 4, and minus 2, 4. I'm just going to list those basic points because I'm going to do just a little bit more than the book did, and it's kind of nice to think of these functions this way. A lot of these basic graphs go through these points with coordinates 0 and 1. Like on this one, you get the points 1, 1, and 0, 0. Right? With an x equals 0, you get y equals 0. With an x equals 1, so that's a very easy line to sketch. And that's a special case of this one, right? You can think of this as y equals 1 times x plus 0. It's y-intercept 0, so it intersects at 0. Slope 1, so you go over 1 and up 1, right? So this is a special case of this one. But y equals x has a 0, 0, 1, 1 on it. This one has 0, 0, 1, 1, minus 1, minus 1 on it. But it's a parabola. You want to memorize it. It's this arch shape, famous in Roman architecture and lots of other places it's used. Even telescope designs and other things. If you make a parabolic mirror, then light coming in parallel rays from infinity all gets focused to a point here called the focus. And you can use that for a solar collector, or you can redirect the light to a little lens out the side and get an enhanced, enlarged image. Used in all sorts of things, radio dishes, electromagnetic radiation. The next one is y equals x cubed. And you should memorize that it looks like this. If you plot a lot of points, your calculator is real good at this. Use the graphic mode and you can see these. And you can make a table of these, x and y. If you put x equals 0 and cube it, you get y equals 0. So it goes to x equals 1 and you cube it, you get y equals 1. Minus 1 cubed is minus 1. So you got all these things. 1, 1, 0, 0, minus 1, minus 1. A lot of these go through these points. Makes putting in a few easy points on the test easy guessing game sometimes. I had a student in a real basic math class one time years ago. He was failing everything, and he couldn't do anything. How did you get into this class? It was well below this class. And what he had done is he had all multiple choice tests, and he could guess all the answers because there were things like 0 and 1. He just plugged them until he got the right answer. Never learned to do the math. You won't be able to do that here, but you will be able a little bit to kind of guess. So there's that one. Y equals x, and this generalization of it. Y equals x squared is a parabola. Y equals x cubed is this thing that looks sort of the same here, but it's a little steeper here than this one. And then it goes down instead of up on the left. And then 4 is this one, y equals square root of x. How about that one? Well, anybody know what that one looks like? I can put all these up at the same time. We actually do have it in the textbook, all up at the same time. So I have, I might put it up here. What does square root of x look like? Remember?
Ooh, yeah, kind of.
Here's a hint. If you were to square both sides, I'll say
Isn't it this?
Hmm?
Isn't it like that?
Yeah, except turn this way. Yeah, that's close. Yeah, y. If you square both sides, you get y squared equals x, and then y squared equals x is like x equals y squared, but going the other way. It looks like this. But there's a trick. When you square both sides, you have to use extra solutions. This includes y equals minus the square root of x negative number, so you have to take this part out. So it's actually exactly the same shape as this part of this one, but going over here. This is what the square root function is. It's like that. And you can plug in a few points and check it. So x versus y equals square root of x. You put in x equals 0, the square root of 0 is 0. Put in x equals 1, the square root of 1 is 1. You can put in 4 and 2. And so you've got 0, 0 here, 1, 1 here, and out here you've got 4, 2, and other points. So it shows you it bends over. It doesn't just go on a straight line. But it's interesting. It has these two basic points here. Maybe we should put this over here. This one has 2, 4, and minus 2, 4. But I think these are the important points for me. Everybody can remember those easy ones. Same thing here. You remember these easy ones, but also know it goes out here through 4, 2, and it's over like that. But it's half of the parabola plotted over this way. It's the square root function. Well, y equals the cube root function. What do you think that looks like? You can cube both sides and find that y cubed equals x. Let's put this in parentheses. And so actually this function is the cube function. Instead of y equals x cubed, you got x equals y cubed. It opens this way. So the axes were flipped. The x and y axes were flipped. And so it looks just like that one, except the whole thing is plotted. It's like this. Here's y equals x cubed. Cube root of x cubed. That one. Then y equals 1 over x. I put these up because these are really, really common functions in mathematical models. And you want to know what these look like and how to do certain things with them, how the graph changes when you do certain things for modeling. So y equals 1 over x, what does that look like? So if you plot a bunch of points, you can see this one. This one is not so easy to deduce from those. These are easy because they're just interchange x and y. This is the same shape as this one, just flip the other way, as though you interchange the axes. And that one is half of, this one is half of that one. So if you put in this one, x versus y equals 1 over x, you can't put in 0, 0 because 1 over 0 isn't fine, but you can put in 1 for x and get 1 over 1. You can put in minus 1 for x and get 1 over minus 1 for minus 1. Those common points are actually on here. 1, 1, minus 1, minus 1. I put these points partly because you should instantly know whenever you see these that these points are on there. I don't know if the book makes a big point of that, but it really helps your graph, you know. If this, you don't want to put 10 here and put this point, it's not at 10, 10, it's at 1, 1, right, but it goes through. So 1, 1. And then it turns out it looks like this. We used to draw these in different colors. It goes like this. And you can kind of figure it out because if you put in x equals 2, y is 1 over 2 is a half. So at 2, it's lower, right? There's 2 a half. But if you put in x equals a half, you put y equals 1 over a half, flips it upside down as 2, right? The reciprocal of a half is 2. So you also get this point, 1/2, 2. And you start seeing if you put in 10, y is 1 over 10 is a smaller number. This is getting smaller and smaller. We can put in some other one. 10 and 1/10. You go way out here, there's a point real close to the x-axis. Lots of others, but the ones I want you to know are these two. 1, 1, and minus 1, minus 1. And then you can just kind of draw the graph through those points, and the x and y axes are actually asymptotes. Sometimes we draw dotted lines here, meaning the function gets closer and closer, and these are called asymptotes. Right? Because you can kind of see it. At 10, you're at a tenth. At 100, you're at 1/100th. This is getting closer and closer to the x-axis. Similarly over here, when you're at minus 10, right, y is 1 over minus 10 is minus a tenth. It's just below the x-axis and getting closer and closer. And similarly over here, it gets closer to the y-axis on both sides. Right? The same way, 1/2 is with 2, 1/10 is with 10, and so forth. So this is the basic graph of the y equals 1 over x function, and this comes up quite a lot too. This is actually used in telescope design also. It's called a hyperbola. So I write a couple names on here just for fun. I don't think they're asking you this in the text. But this is an example, not all of them. It's an example of a parabola. This one is an example of a hyperbola. And these are the most basic parabolas and hyperbolas. And it turns out by using the techniques we're going to be introducing today, you can sketch every hyperbola with vertical axes by just stretching and shifting this one. And you catch every parabola that's vertical like this just by stretching and shifting this one. So these basic ones with very simple equations are actually very important because you get the others by stretching and shifting. All right, 7, they give you this one. This one is not as important, but we should see it. The little y equals 1 over x squared. What does that look like, do you think? Again, you can plot some points on it. You get some similar things here. If you put in the real simple numbers, you can't put in 0 because you can't divide by 0, but you can put 1 and get y equals 1 over x squared. Y equals 1 over x squared. 1 over 1 squared is 1. If you put in minus 1, 1 over minus 1 squared is again 1. Those are important points you should always recognize this function. So 1, 1. These basic functions go through 1, 1, or minus 1, 1, or minus 1, minus 1, minus 1, or 0, 0. It's amazing when I thought about it years later. All these basic functions have some real common points. So it goes through this point and it goes through this point, but the graph actually looks like this. So plotting a graph that has this kind of shape and goes through these 2 points gives you an idea what its behavior is. How do you know it has that kind of shape? You let your calculator run it. It calculates a whole bunch of points and plots them, and you just look at it and see. But we can plot a few. These are the 2 important ones you should know. Just if you know these 2 and know the shape, you can sketch it, right? That's why those are important points. Same thing in here. If you know these 2 and you know the shape, you can just sketch it to approach the axis and go through those points. This one, you make it through these 2 points and make it kind of bend over like a half parabola. That's the idea of all of these. But if you want to make it more accurate, you can put x equals 2 and get y equals 1 over 2 squared is 4, and also at minus 2, 1 over minus 2 squared is 4. So we can plot, 1/4. And so I can plot out here 2 1/4, minus 2 1/4. We don't need those. Those are just extras to make it a little more accurate. But when you start plotting a bunch of these, you start to see the shape come out. If you put in a half, then 1 over a half squared is 4. So you can put 1/2 4 for minus a half 4. Just plot these 2 and plot this shape. Right? And then there's another one. This one is the absolute value function. Y equals absolute value of n. How is the absolute value defined? Well, it's given this piecewise definition. I don't know if you've seen piecewise definitions before. We have to talk about those today too. We'll see how much time we have. But the absolute value of x function is the function if you give a positive value of x or x equals 0, or just returns x. So we write it this way, meaning if x is greater than or equal to 0, this is really just give x back. And then if x is less than 0, the rule is to give minus x back. Now, if you think about it, if x is negative, then minus x is positive at the same size, right? So this is a size function. It tells you how big x is, how far it is from the origin. And it's got this definition. Piecewise. Now I know exactly how to graph it. And amazingly, your book has a major blunder in it. Next, on page 276, there's an error in the graph. It's wrong. I don't know what happened. So we slipped the bad thing in it. This textbook is widely distributed. But this one I just pasted in the wrong graph. How can we sketch this graph? Y equals x if x is non-negative and minus x if x is negative, right? You want to sketch that one? Oh yeah, you got it. It's a V. Here's how you do it. It's for the x values that are non-negative, and these are the x values where x is at least 0, right? This half plane, right? All the x coordinates you drop to find the x coordinate. Take any point, drop the vertical to find the x coordinate. It's always non-negative, right? In the right half plane, we sketch y equals x, right? If x is greater or equal to 0, then y is x. So we sketch this, but what's this? Erased it, of course. It's that line, right? It's the line that splits the two axes and looks like this. So we sketch this thing. That's where this comes from, right? And then for x less than 0, let's put it over here. That's these x coordinate over here. In this half of the plane, whatever point you take, find its x coordinate by dropping a perpendicular. And it's always x less than 0. So this is all the points where x is less than 0. In this half plane, we sketch instead this line y equals minus x. And that one is different. We haven't done that one yet. But we have. How do you sketch this one? Rewrite it equivalently as y equals minus 1x plus 0, right? That's the same thing. Minus 1x plus 0 is minus x. Oh, it's y equals mx plus b, right? Slope minus 1, y-intercept 0. So it goes through y-intercept 0. And then has slope minus 1. So if you go over 1, it goes down 1. So if it comes here from minus 1, 1, it goes over 1 and down 1. But over here, slope is 1, it goes over 1 and up 1. And you can plug in points to see, right? If you plug in x equals 1, absolute value of x is 1, right? If you plug in x equals minus 1, the absolute value is minus a minus 1 plus 1. So it goes through both these points, minus 1, 1, and 1, 1. But the graph here is a line of slope minus 1, y-intercept 0. So it's just this line here, but you only plot it in this half plane where x is negative. Avoid 0 because it's only for x negative. But then here you fill in 0 by plotting the point and go this way. So you plot a half line. This half line, y equals x to the non-negative coordinates. This half line, also called a ray is a half line, for x less than 0. Sometimes, but technical terms that try and teach x in terms in history related classes. This one you don't include 0, 0, right? Because it's only for x less than 0. We call this an open ray because it doesn't include the endpoint. This one we do include the end because it includes x equals 0. We plot like this and call it a closed ray because it includes the endpoint. But you don't need to know that for the test. But between the closed ray and the open ray, we plot this V shape. That's the absolute value function. Y equals absolute value of x. Like I said, this one's plotted wrong in the book. I shifted it down and get an x. All right, so those are the 8 basic functions that quite a large number of algebraic graphs are based on. There's lots more in trigonometry and so forth, but these are the basic algebraic graphs. We'll do some more as the semester goes on. Now for modeling, we want to be able to do some things with these. We want to translate, also known as shift. These will mean the same thing for us. You'll see both words used in the book. These, move them to other positions. And we want to be able to stretch or compress these. And we want to construct piecewise functions from these, such that the absolute value is really defined piecewise. But all those are useful. These piecewise defined graphs, you say, who needs these piecewise defined things? That's actually what they give a couple examples in the text. The way they define things like tax tables, you find they're actually piecewise lines if you plot them. That kind of thing is very common. A lot of times in modeling, if you got a rocket going through the air and you don't know what points are in between, just for a quick approximation, you might draw a line between and say, well, you know, if this is time versus altitude or something, you can say, well, it was approximately here at this time because it's halfway, you know, between those 2 points right there, right? So it's used quite a lot in simple interpolation of data. You can say tax tables and other things where they don't want to complicate. And so first we want to do translations or shifts. the graph of a function y equals a known function f of x, maybe one of these basic graphs, plus a number b. Nice to use the same way. Bring it back up because I think I closed it. You want to use the same letter here, sorry. By the way, maybe I should put this on the screen here. Or here, now that I have it up. Here are some better plots than I can do by hand of your base. Here's the graph of y equals x squared. That's what a parabola looks like when the machine plots it. Here's y equals x cubed when the machine plots it. Here's the square root of function. Square root function. See, it looks like half of this one flipped over. Here's the cube root function, right? Cube root of x. Here's the 1 over x function. Looks just like that. So you go through 1, 1, and minus 1, minus 1. Here's the 1 over x squared function. I got the other. Now the square root function is shifted down, or the absolute value is shifted down for some reason. Here's y equals x. So those are the basic functions that I list. And now, the letter they use here is I forgot. Lots of problems for you to work on there. H they use, not B. K they use. Right. K. The graph of y equals f of x plus k is, as you can guess this, graph of y equals f of x does what to it?
Just shift it up one.
Okay, just add k to every y coordinate, right? So shift it up k units. In y. So if I were to give you this kind of simple example. Sketch y equals x squared plus 1. What does that look like? I start with the basic graph y equals x squared. And I know the points it goes through, 0, 0, 1, 1, minus 1, 1. And maybe I want to plot some more just to be real accurate. I'll plot 2, 4 or something. Then I'll say the one I want is just add 1 to every y coordinate. So I plot, add 1 to this y coordinate, get 0, 1, and 1 to this y coordinate and get 1, 2. 1 over here makes it minus 1, 2. And then 2, 4 becomes 2, 5. Add 1 to every y coordinate, draw exactly the same shape. Shape doesn't change at all. And it goes like that. And everywhere it's just 1 unit above. Right? That's all there is to run y equals x squared plus 1. But this is what it does to any graph, not just the x squared. Then, slightly harder. B, the graph of y equals f of x minus, I think these h probably, check, these like h and k. Oh, it's a plus h. All right, I like minus h. I'll follow the book here and got their notation here. How is the graph of f of x plus h related to the graph of x itself? The graph of y equals f of x, I'll give you a hint, it's translated or shifted, moved. Translate the same thing. How does that one move?
Isn't it to the right? On the
Yeah.
x-axis.
If it was minus h, it would be. Since they put plus h in here, we're gonna say it moves it. I'll make sure they follow through. Right. She's a new textbook to me this semester.
Let me see this.
They might do both here because they did that with the K. Yeah, they did it both. Let's just do this. F of x plus k is the graph of this one. Instead of saying shifted up, we'll say shifted k units in y. So it can be up or down. If k is positive, it's up. If k is negative, it's down. So get rid of the up, say move k units in y. And then I can replace this the way I like to see it, which I think is y equals f of x minus h is the graph of y equals f of x. Move h units in x. And if h is positive, it actually moves to the right. So it's the subtraction that it's whatever subtracted is a shift. About that. For instance, if I take the parabola y equals x squared, right? And then I say, I wonder what the graph of y equals x minus 1 squared is. What you're thinking of this is here, this is f of x is equal to x squared. That's another way. Right? Here, f of x, this is f of x minus 1. Right? If f of x is the squared graph, f of x minus 1 takes whatever's x and put parentheses and square it, right? Give any number to this function, it squares it. So if I put in x minus 1 instead of x, I have to square x minus 1. That's this function. So if this function is the same as this one with x is replaced by parentheses x minus 1, what happens is the graph just moves 1 to the right and it looks like this. You add 1 to every x coordinate and it's the same shape, just add 1 to x. And so instead of the basic graph, remember, went through 0, 0, 1, 1, and minus 1, 1. We add 1 to every x coordinate and we get, well, 0, 1. Right? We get 1, 0. And we get a parabola of the same shape, 2, 1. Adding 1 to every x coordinate. If you want 2, 4, it becomes 3, 4. Add 1 to every x coordinate and it's the same graph otherwise. That's what this one is, x minus 1 squared, where you just take what was squared, x, and replace it with x minus 1. That's what this notation means. It means wherever you see x in the equation, replace it with parentheses x minus h. That moves that one to the right. And here's why it works, right? If you think about putting in a table of these, you have to make x 1 bigger to square the same number, right? So it's moved 1 right, and you have to make x bigger to get 1 bigger to get the same y. Here, if I put in x equals 1, I get 0 squared. It's the same I used to get when I plug in x equals 0 here. As I put in 0, I get y equals x squared, 0 squared is 0. Here, y equals x minus 1 squared. I put in x equals 1, and I square 0. If I put in x equals 1 here, I squared 1 and got 1. But here, I put in x equals 2, then I take 2 minus 1 squared again. You have to put in x1 bigger on this one to square the same number. And the same thing with any graph, you have to put in x bigger to get f of the same number and get the same y value. But you have to make h bigger to get the same y values, and it moves the h units to the right. And it's whatever is subtracted, that's the trick. And this one is whatever is added to y, right? Because you're adding to every y coordinate, but that one is whatever is subtracted from x. Let me give another example because this one's slightly trickier like that, right? Suppose I said sketch y equals absolute value of x minus 3. What does that look like?
What did it mean?
Shape move to the left 3 times.
Yeah, we start with the basic graph, y equals absolute value of x. And then we replace x by x minus 3. If we call this f of x, the basic graph, then this is f of x minus 3 because I just took x and replaced it with x minus 3 everywhere. Right? Y equals, and I do the same thing, but I replace x with parentheses x minus 3. And that's this function. You can drop the parentheses, they don't do anything. But this graph now is the same as this one, shifted 3 units by this comment we went over here. You have to make x3 greater to take the absolute value of the same number you did before. So instead of 0, 0, x has to be 3 greater, and then you'll take the absolute value of 0. 1, 2, 3. So the v is right here at 3. If you put in x equals 4, the absolute value of 4 is 1. You get 4, 1, 3, 0, where you used to get 0, 0, and 1, 1. Right? Here, when you put in 1, you get absolute value of 1. Here, you have to put in 4 and get absolute value of 1. So forth. It's actually the same shape, just moved over 3 units to the right. Right? So it's what you subtract from x. That's the shift. I say, oh, that's just the absolute value function with x replaced by x minus 3. But it's the absolute value v moved over 3 units to the right. Subtract.
Why does it go to the right, not the left?
Yeah, it's because you have to make x3 greater to get to take the absolute value of the same number. So when you make, right, if x is 3, I'll take the absolute value of 0. Where here, if I put in x equals 0, I get x. Take the absolute value of the same number. On this graph, I have to make x3 bigger, so I have to move it over this way. You get the bottom of the v, for instance. Right?
So if you're subtracting, it goes to the right. And
Yeah,
adding
whatever you subtract is, moves that far to the right. The other one's easier. You add, it moves up. That makes sense.
Yeah.
Here you subtract, it moves right. You have to make x3 greater to get the same y value. But this actually comes up quite a lot and is fundamental in the graphs. A lot of them in calculus and so forth. If you're taking that, a lot of you may finish after algebra trig. But in calculus, they give you graphs all the time, and they expect you to have a handle on what they look like, and they expect you to know these techniques. Suppose I wanted to sketch now y equals absolute value of x plus 1 plus 2. What does that look like? I can sketch that easy as can be. Actually, a lot of calculus students come in and can't do this. You'll have an advantage if you remember this. Sketch that.
the left one up to.
Yeah, exactly. I made 2 translations for that one. I start with the basic function y equals square root of x, just because I see the square root there. That's the half parabola. Then I take that to, I say, what does it look like if I replace x by x plus 1? What y equals square x plus 1 look like? How do I get this function? This is the same thing as taking the square root of x minus a negative. Right, so I've taken this one and replaced x with x minus this number. The shift is minus 1, so it moves it 1 to the left. All right, in any equation, if I replace x by x minus a number, it shifts at that many in x. So I'm shifting a minus 1 in x. It actually moves it 1 to the left, but it looks like this. So instead of going from 0, 0, and 1, 1, it now goes through 1 less on each x, minus 1, 0, and 0, 1. Just subtract 1 from each x one. That's what that one looks like. Well, I'm only halfway there. Now I want to add 2 at the end. So I'm going to do one more graph. I just have to do a shift in x and y. If I add 2 to every y coordinate, it's going to move it up 2. That one's the easy part. So now I add 2 to every y coordinate here. Instead of minus 1, 0, I get minus 1, 2. Instead of 0, 1, I get 0, 3. And I draw exactly the same shape as the beginning because all I did was move it, right? Translate it, shift it, move it, all means the same thing. I take the same shape and I just draw it through those points. There it is. Here's y equals absolute value or square root of x plus one, this one, which I wrote like that just to show you that, plus two is a shift, the last one, plus two in y. So in y, it's whatever's added at the end is the shift. And in x, it's whatever is subtracted from x when you replace x by x minus the number. So it's actually our basic square root function just moved in the plane. That's all this function is. And you want to recognize what we said. Oh yeah, I can just move that. Those are the one I memorized. And those important points are real nice. What always happens at the end of the in the period of hard ones start coming. Right? Now the Macaulay Culkin line applies. I love it. That movie, right? Had enough. Are you thirsty for more? You said that so well. Now part two is to do stretches and compressions. This is a little harder still, but once you're done with these, you'll feel like an accordion player or something doing your graphs. It's terrible. All right, stretches, compressions. The graph, like my finger down, didn't wake it up. The graph of y, and I forgot what letter they used here. Go down. Box. A. All right. The graph of y equals a times f of x, where a is a number, is the graph of y equals f of x, except it's scaled by the factor absolute value of a. So it's absolute value of a times as large for all the y coordinates, if you think about it, right? If f of x was 1 before and a is 2, then it's 2 times y is twice as large. If f of x was 1 before and a is 3, it's 3 times 1 is 3, it's 3 times as large, right? Whatever you multiply it by scales the y coordinates away from the x-axis to be 2 or 3 or however many times as large. Let's scale by absolute value of a. And what if a is negative? It had a positive coordinate, it's now negative, right? If you had a negative coordinate multiplied by negative, it's now positive. So it flips it upside down. But it's also, this is my symbol for and, flipped upside down. I need to get it in the time. I'm still have a finger down here. And flipped upside down if a is negative. Meaning flipped over the x-axis. They may have put one for minus a and one for plus a and assumed a was positive. I prefer to put this down. And if a is positive, it doesn't flip it. If a is negative, it does flip. They'll put a or minus a, I think, as I recall reading it. And in that case, they assume a is positive all the time. It's a scaling factor. I like to put it this way. Absolute value of a is a scaling factor. Flip it if a is negative. Now this is scaled in y. Vertically scaled. Because it's multiplying the y coordinates by that number. Call that A. What about horizontal scaling? The graph of y equals, check their lettering again. do that one. Okay. Yeah, instead of the word flip, they use reflected, flipped or reflected, same thing. I'll just leave it. I'll make this comment. The graph of y equals f of ax, where you place x by ax, is the graph of y equals f of x, except now x has to be 1 over a times as large to take f the same number. So it's scaled by 1 over a. Absolute value. And flipped horizontally. Flipped reflected. Over the y-axis. If a is negative. And this is actually true not just for functions, but for any equations relating y and x. If you replace x everywhere by ax, it will scale the graph by 1 over absolute value of a horizontally, and flip it horizontally over the y-axis if a is negative. Similarly here, if you think about this one, this can also be written y over a equals f of x, and this also scales it by 1 over a in the y coordinates and flips it if a is negative. So you can, there's a nicer way to write this for general equations is the point, but we'll just do it this way. So a multiplying a function by a number a scales it by absolute value of a and flips it if a is negative. Replacing x by ax scales it by 1 over absolute value of a and flips it horizontally if a is negative. The idea is if a is 2, x only has to be half as large to get the same y value. If a is 3, x only has to be a third as large to get the same y value. And so it scales it by 1 over a, right? If you get a 3, the graph is 1/3 as high. Or excuse me, it's stretched 3 times, 1/3 as much. And I say scaled, meaning it can be a stretch or a compression. Right? Well, let's do a simple one here. G of x equals 3 cube root of x. What I wanted to sketch by hand, the calculator can check you on all this too. You've got to get a math calculator using y equals 3 times the cube root of x. There's another basic function, the cube root. Right? The idea is I know how to sketch the cube root. What is 3 times the cube root? Like it's easy. That's the answer. Just what you do is you start with the basic graph. Y equals cube root looks like this. It's the cube function turned sideways, remember. And how do I get 3 times the cube root? Well, that's just 3 times the original function. I think of this as f of x. I want to sketch y equals 3 times that f of x. So what does it look like? Well, it just takes every y coordinate on this graph and multiplies it by 3, so it's just 3 times as tall. When you memorize these important points, 0, 0, 1, 1, minus 1 on the cube root function, all we do is multiply each y coordinate by 3, right? In the shifts, we just added to each y or x coordinate or subtracted. Here now we multiply each y or x coordinate. That's the scaling. But I'm going to scale it by 3. I'm going to make it 3 times as tall, and it's going to go through. It's not going to be the same shape anymore. It's stretched, but it's going to look the same shape, but stretched 3 times as tall. So it's going to go through 1, 3, multiplying every y coordinate by 3, and it goes through that point 1, 3, and this point minus 1, minus 3. Multiply both the y coordinates, and 0, 0. I multiply the y coordinate by 3 is still 0, right? So it still goes through that point. And what happens? If you think about it, on these stretches, it pulls it around the x-axis. Each point is pulled 3 times as far away from the y-axis. All right. The y coordinate is 1, now it's 3. If the y coordinate is minus 1, it's now minus 3. Right? Well, that's what the stretching does on there. Effort, yeah, okay. H equals minus a half absolute value of X. Catch. H of X equals minus a half times the absolute value function. What does that look like? So this one was a stretch because the scaling factor was greater than one, right? This one, A, multiplying the basic function, has your scaling factor is absolute value to that is 1/2, so it's a compression action. It's going to be half as tall. 1/2 times the absolute value of function is half. The minus flips it upside down. Flips over the x-axis. Upside down. So that's all I have to do, and you can picture this in your mind is what's beautiful about this. You know the absolute value goes through these functions, these points. 1, 1. Minus 1, 1. Right, because absolute value 1 is 1, and absolute value minus 1 is 1, and it goes through 0, 0. Now to sketch this one, I take every y coordinate, multiply it by half, and then flip it upside down. In other words, I multiply it by minus a half. I get this point, instead of 1, I get minus a half for y, with the same x coordinate. This one, I multiply the y coordinate by minus a half, I still get 0, so I get 0, 0. And this one, I multiply the y coordinate by minus a half and get minus 1 minus a half. And look what I get is the same shape, but compressed. It's only half as tall, right? Because it's not the same steepness. Something like that. Minus 1 minus a half. So half is far from the y-axis and pushed upside down. A lot of these things out of 2.3, I haven't quite finished the section. We have to do the piecewise function still, but I think you can start on it. All right, go have a really nice weekend. I'll see you in the future.
Did you go golfing with him? Did you go golfing with him? Going right now.
What time do you go to school? Me too. I gotta go get shot.